Thank you for joining us for the today's webinar on smart self-healing CRP composite. Myself, Dr. Chirajit Bhaumik, working as an assistant professor in the Department of Mechanical Engineering, Parole Institute of Engineering and Technology, Parole University. Parole University is a self-financed private university and one of the leading universities in the state of Gujarat. So, without wasting much more time now, I would like to request Dr. Nazrul Islam Khan sir on behalf of Parole University for the today's webinar. In this regard, I would like to introduce the today's expert as Dr. Nazrul Islam Khan has completed his BTech from Guwahati University with first class and honors and did MTech in materials and manufacturing technology from NIT Silchar. He has completed his PhD on Thermo Reversible Self-Healing CRP Composites from NIT Silchar. He published more than 20 international and national peer-reviewed journals and 8 conferences, 1 self-edited full book and 1 book chapter. He has filed 1 Indian patent. Dr. Khan has 6 years of teaching and research experience in the field of nanotechnology, nanocomposites, multi-scale laminated composites, smart materials, adhesive joining of similar and dissimilar joints, self-healing CFRP composites, base materials, building materials, etc. Currently, Dr. Khan is working as a senior assistant professor, Department of Mechanical Engineering, GMR Institute of Technology, Rajam, in the state of Andhra Pradesh. This institute is an autonomous institute of GMR Infra Group. Now, Dr. Khan is also a life member in the position of associate member of institutional engineers. So now I request Dr. Khan sir to instigate the session. Sir, the session is yours.
Thank you so much, Dr. Chiranjeev. Let me first share the screen.
Yeah, sure, sir.
Is it okay to stop the video?
Yeah, definitely. Yeah, sure, sir. Yeah. You can.
Yeah.
Just enlarge the screen, sir, and just okay. Now it's not.
Yeah. I stopped actually that sharing.
Yeah, sure, sir. Just share you.
Can you see the shared screen right now?
Yeah. It's purely visible, and you are absolutely audible over here.
Okay.
And this session is, sir, for your information, this session is right now live from our Facebook profile, from our University Facebook webinar page. Okay, sir, you can continue now.
Okay, thank you, Dr. Chiranjeev Bhaumik and Dr. Sumit and your team from Parole University Mechanical Engineering Department. Thank you so much for giving this opportunity to deliver a talk on this topic, that is self-healing CFRP composite. So as you know that till now that human being, we can heal if any crack, any scratch on our body, we can heal. But we did not know that the materials also can heal itself. So that is what today I am going to discuss in today's lecture. So this self-healing CFRP composite, before going in depth of that, I will be introducing the art of surface functionalization and how to characterize them and their application in various advanced materials. So as already introduced by Chiranjeev, so I'm not going to introduce again, so I will directly go to the outline of my presentation. So the outline of my presentation, I will cover the surface functionalization of various nanomaterials for their application in composite materials. I will be in very brief of this topic because already some expert speaker has touched this topic. Then my main focus will be on smart self-healing CFRP composites, as well as I will cover the biocomposites and materials, metallic substrates for better adhesive joining. So for all these, I need to discuss the surface functionalization first. So let us start with the surface modification. So as you know, the surface modification is the act of modifying the surface, right? So act of modifying the surface to change the physical and chemical properties of that surface. Okay. So generally suppose if you consider person A and person B, they are not having a good relationship. Suppose they have some enemy or some negative sense. They are not in good relation. So if they have a common friend like a zeroth law of thermodynamics, if A is in equilibrium with B and C is in equilibrium with B, then we can say A and C is in equilibrium. So whatever that B is acting in this role is to get that physical or chemical bonding between A and C. So with respect to zeroth law also we can relate this thing. So this surface modification is not only can be done for solid materials, this surface modification can be done for liquid materials as well. So if you take the example of lotus, so the role of surface modification, you can see that the nature is also taking the advantage of surface modification. In what sense? Let us see. If you see that the wing of butterfly or the leaves, they don't get wet due to any rain or water. So what nature? Why they are not getting wetted? Right. So because if you in high magnification image, if you see the surface image of this butterfly or a lotus flower, so you will see that lot of hills, or you can see lot of finger-like structures can be seen on their surface. So due to the presence of those surface textures, the surface energy between the water droplet and the surface becomes very, very high, so they does not easily get wetted, right? So again, you know, if you again ask you what is why it is not getting wetted and what is the advantage of that. So basically what is there in case of lotus leaf or something, so whenever any dust particle is there on the surface, it reduces the photosynthesis to take place, right? So whenever this water comes in contact on the surface, due to the large surface area, the water droplet takes the complete bubble shape. And as you know, what is their adhesion and cohesion, these two mechanisms is going to take place. So adhesion and cohesion, if you go in depth of what is cohesion, so generally it is an electrostatic attractive force between similar substances, right? So if you assume any particle which is inside of the water, so it is surrounded by only water particles, so it will be a good, whatever the force acting here is cohesive force. Now what about any particle which is on the surface? So on the surface here, since it is the attractive force between the surrounding and two dissimilar substances, so there your adhesive force is taking place. So due to that, this adhesive and cohesive combination of this, there is a high surface tension, and due to that the water droplets takes the spherical shape, and when it gets the spherical shape, and whenever it comes in contact with any dust particle that is present on the surface of this leaf, it carries takes that dust particle, but it will not wet the surface. So it will be helping as a self-cleaning of the this butterfly wing, or you can say the leaf of lotus. Okay, so this is the advantage how the nature has adopted the technology of surface modification for their self advantages. So some nanotechnologies have developed this kind of treatment like coating, paints, roof tiles, fabrics and other surfaces, and can stay dry, clean themselves by replicating in a technical manner in self-cleaning properties of plants as the lotus plant. So whatever how the water bubble is taking this spherical shape, so here what is happening, your super hydrophobic nature is becoming where the contact angle, I will show you in later slides what is contact angle, and this contact angle becomes very, very high, and the surface and that water becomes super hydrophobic in nature, and which is helping for self-cleaning purpose. So this technology can be adapted for various applications. Okay, the modification of different surface can be done in our different intention, like to give intentionally give some roughness, or suppose you need to change the surface characteristic from hydrophobicity to hydrophilicity. So you can convert that by changing the surface materials. Or if you want to change the surface charge or surface energy, then we can take the help of some other foreign materials on the surface, and which will give those kind of intentional properties. Okay. So this surface functionalization introduces chemical functional groups also. And most easy method is that generally, if you want to change the surface properties, then you have to add some chemically, you can select the chemical group to modify the surface functionalization. Okay. So these are the technologies where it can be easily functionalized with different chemical groups. It may be hydroxyl group, it may be epoxy group, it may be ketone group, it may be different functional groups as per our requirement. Suppose we need charge, then we need to go for some free electrons, double bonds. So those things we can easily add on the surface of the nanoparticle. Okay, so in case of polymer also, there are limitations in application of nanomaterials. In case of the field of nanotechnology, the nanofillers, they have very, very high surface energy. And that's why these nanomaterials don't try to, they have, they don't have the interaction, good interaction with the matrix material. So the polymer matrix, whatever it is, they don't have a good interaction or bad wettability, you can say. So to increase the good wettability of the nanofiller with the matrix, or to incorporate some certain electrical or some thermal properties in the material, we can go for this kind of functionalization. So surface functionalization, and it is very interesting, please go to this point. Surface functionalization can tune their properties in nanoscale. Okay, if you want to get some desired properties from the bulk material, and for that the first most important point is that if you can tune their properties in the nanoscale, then that will be, scale up to very high when you get the bulk material. So that is why we generally play with the properties of the nanofiller in the nanoscale itself, and finally we get we harness the good mechanical properties out of the material. It also provides a means of further grafting, and as well as I told you, A does not has the intention to make friendship with C. But if you have a common friend B, then maybe that A is having some friendship with C. That's why it helps to further grafting or conjugating some other materials on the surface, right? So for that, let us first discuss one of the surface functionalization technique, that is selenization of carbon-based nanofillers. And this topic, one of your previous speaker has talked already, but it is required for to discuss to introduce my topic, that is smart self-filling materials. For that, I have taken this topic as well. So as you know that for suppose if you want to add A with C, B is required intermediate. So that's why suppose our intention is that we need to attach epoxy group on the surface of any carbon-based nanofiller. It may be carbon nanoparticle, it may be graphene, it may be graphite nanoparticle, it may be fullerene, it may be whatever it is carbon-based nanoparticle. So for that, we did oxidation of that, so that we can introduce some oxygenated functional groups like OH group or ketone group or carboxylic group on the surface. And this carboxylic group, when we add with the silane group, okay, so suppose here we have used APTES, amino propyl triethoxysilane, or GPTMS, glycidoxy propyl trimethoxysilane. These are some surface functionalization group, and which is having end group is your SiO and NH2, okay. Or in GPTMS, it is having epoxy group and SiO, this one. So this CH3, and here what is the oxygen hydroxyl group present, this CH3 and hydroxyl group will form a covalent bond and get removed as ethanol, and finally we will get a structure having the end product as epoxy group. So this epoxy group now in my area, as a given the example of A, B, C, but in my self-filling I needed A plus D plus C plus D, because I could not attach directly A with D. Okay, So that's why I have taken the help of intermediate two products, two functional groups. That is, first of all, oxygenated functional group. Next one is your epoxy functional group. So what they have the advantage, we will discuss later here. So here you can see it is a very simple setup where we did this oxidation in a nitric acid solution, and then we have taken an aminopropyl trioxysilane or glycide oxide propyl trioxysilane. So these are two methods having amine or epoxy group at the end. So this can be functionalized easily. So after functionalization, we have observed that their surface properties can be significantly changed. Okay, if you see this A1 and A2, we can see lot of agglomerated graphite nanoparticles or carbon nanoparticles, you can say. But once we go the oxidation and selenization with them, they get de-agglomerated. Okay, they get de-agglomerated, and de-agglomeration is very much required to harness better mechanical or thermal or electrical properties. If the nanofiller itself is agglomerated in the matrix form, then we cannot harness those mechanical properties. So for that, one advantage is that it is giving some exfoliation or de-agglomeration taking place. Next, what is happening? So these are some chemical characterization. You know that how to characterize whether successfully this functionalization has taken place or not. For that, we can take the help of FTIR, Fourier transform infrared spectroscopy, or Raman spectroscopy, where we have from the FTIR we will have the characteristic peaks which will signify that the APTS or GPTMS is present on the surface of graphite. Okay, like here you can see 1090 and 910 centimeter inverse. This is the wave number which are corresponding to the epoxy ring. So that means we can confirm that epoxy has been present on the surface of graphite nanoparticles. So this is the indication of successful functionalization. Next, also another indication is that in case of pure graphitic nanoparticle, the defect band and graphene band, the ratio of defect by graphene, defect band to graphene band, graphite band is very less. I mean, defect is very low. But when we add those foreign materials on the surface, defect intensity becomes high, and due to that, you can see the ID by IZ ratio increases with respect to different functionalization methods. Okay, so this is also indication that successful functionalization has taken place. And this is again very simple example that transmission electron microscope on the surface. You can see a very uniform layer has been deposited on the surface of graphitic nanoparticles or carbon nanoparticles. So this is also will give you the indication that yes, successful functionalization has taken place. And another very simple technique is that if you want to do any kind of functionalization, first of all find it out what is the polarity nature of the filler, and accordingly you select a solvent and you try to disperse them. Okay, so if there is a good polarization, I mean if the polarity matches with the solvent, if it is successfully functionalization has taken place, it will not get settled. But if it has not been functionalized, then it will get settled. So this is one kind of testing that is called dispersion test. Also, it can give the indication that successful functionalization has taken place. Another, I have given another example is the thermogravimetric analysis, TGA analysis. This also can help you whether successful functionalization has taken place or not. And how we can see this black line here is the degradation. I mean, if you apply any heat or give any temperature to any substance, the weight gets reduced, right, due to evaporation of different materials. So what will happen if you record the weight loss with respect to rising temperature, we can determine at what temperature which components on the surface of the material has got evaporated, right? That we can determine from the TGA analysis. So if you see the carbon particles here near about 100, one simple one-step degradation can be seen. So this step degradation is mainly due to the removal of moisture present, because you cannot take any substance moisture free. If you keep in air, it will definitely absorb some moisture. So due to removal of those moisture, because we know that water evaporates near about 100 degrees centigrade. So due to that, we can come to the conclusion that near about 100, this temperature degradation is due to removal or absorbed moisture. But once we do the oxidation, you can see there is a degradation. First started at near about 100, but it was continuous throughout the process, because although the first degradation was due to the removal of your absorbed moisture, but since due to oxidation there are some oxygenated functional groups attached on their surface, it will continuously get evaporated, and due to that the red color line, continuously the weight loss will take place due to increase in temperature. Now coming back to the ZPTMS or epichlorohydrin treated, ZPTMS or epichlorohydrin 2 functional groups having epoxy ring at their end. Okay, so this blue color you can see here, 3-step degradation can be seen. The first step degradation is due to the removal of absorbed moisture. Second step degradation is due to the removal of oxidized functional group or oxygenated functional group. And third step degradation, which is near about 400 degree, this degradation is mainly due to the removal of epoxy ring. Okay, so if you know that at what temperature which substance get evaporated, from this testing or characterization tool, we can easily determine that whether successful functionalization has taken place or not. Okay, this is a very simple tool. So due to the functionalization, we have seen that before applying them for the next step, first we prepared some composite and tested their mechanical properties, and have seen that the ZPTMS functionalization has the capability to increase tensile strength by 36% and 28%. Okay, so first of all, we got that not only from physical characterization that it has been successfully functionalization has taken place, but from the mechanical characterization also we got the indication. Because why? The epoxy ring present on the surface of this nanofiller, this epoxy ring will form some covalent bond with the amine group, which is present generally in case of any polymer matrix. Whoever working in this field, they will be knowing these things. So this amine and epoxy will interact and will take more load, if any, from the filler and matrix. If it is having good covalent bonding, then whenever you apply any load, that load will be transferred from matrix to filler, and it will absorb more energy before any fracture takes place. Okay, so it will divert the crack in random directions, and you will get more energy out of the composite, and due to that your tensile properties or any other mechanical properties get improved if you do this kind of surface functionalization. So like a flexural properties, it is, you know that flexural properties means bending property. If you or outline mechanical properties, it can be said. So this also increases due to addition of this epoxy group. So why I am going to discuss this, I will come to that later once we start the self-healing part of my discussion. So that from the surface fracture analysis, we can see that if you give any without surface functionalization, if you add this graphene-based nanoparticle, then there is, you can see the graphene nanoparticle can be seen as a agglomeration. But when you can do this kind of surface functionalization, you will not see those kind of agglomerates, and it will be uniformly dispersed. So this is again very advantage of this surface functionalization. Next, coming back to other technology, what can be helpful for this kind of surface functionalization? Okay. Now, as I told you, I am discussing the self-healing CFRP composite. What is the full form of CFRP? Carbon fiber reinforced polymer composite. So, if you want to improve any properties of carbon fiber reinforced polymer composite, either you have to change the matrix material or you have to change the fiber property itself to get a better interfacial adhesion between the matrix and the fiber. So, whatever the techniques that I have discussed before this slide, that was matrix modification, because if you add filler in the matrix will be having stronger or steeper, and it will take more load, and that load will be transferred to the fiber, and finally we will get a better properties from the CFRP composite. Now another technique is that you can deposit those nanofiller on the surface of this carbon fiber reinforced polymer composite. Recently we got this some proposals also from some foreign universities. They are looking for a postdoc fellow and something where they need a very fast development of this glass fiber reinforced polymer composite, where the glass fiber can be surface of the glass fiber can be modified by using some certain nanofillers. Okay, so one of the technique is the electrophoretic deposition. So what is electrophoretic deposition? So what will happen if you give, if you disperse the charged your filler in the matrix, and if you add the fiber, that is carbon fiber, in one electrode, and in another electrode you use some copper electrode or some other conductive electrode, what will happen? These charged ions of the nanofiller will be attracted towards the surface of the carbon fiber, and the surface of the carbon fiber will be functionalized using this kind of nanofiller. So you can see here, this is very simple setup for this kind of functionalization. This is a carbon fiber, this is electrode, and once you pass any high voltage along this two electrode, this carbon fiber will be deposited. This black area is carbon fiber, carbon nanoparticles deposited carbon fiber. So if you change the surface properties of carbon fiber, then also you can change the mechanical properties of CFRP composite. Okay, so from this surface characterization of carbon fiber also we can have that. See, we can see that this is the picture, the last picture you can see the roughness, and the first picture you can see that there is a significant change in surface morphology, and this significant change in surface morphology is mainly due to the attachment of those carbon-based nanoparticles on the surface of the carbon fiber. Okay, here also AFM, if you do the atomic force microscopy also, you can see that how the surface roughness has been increased. Okay, here I have not given any data. I will skip this thing. And you can see due to, now again, at what extent you need this deposition of the nanofiller, it will depend what is the applied voltage is. If you increase the voltage, then you will get better deposition. Again, there is a limit. If you get that limit, and if you cross that limit, there is a chance that the fiber will get burnt, because you cannot add very high voltage. So to optimize that, you can play with the voltage and see, and correspondingly you prepare the composites. And what type of composite we wanted to see what is the bonding between fiber and the matrix. For that we have prepared transverse fiber bundle test, TFBT test, where the fiber was kept in transverse direction and the matrix was poured along the silicon rubber mold, and once it flows over the cavity, this TFBT test, once you test it, there is a transverse load on the surface of the fiber. So if you have better adhesion, then you will have good tensile properties. If you have poor adhesion, then the tensile property will be reduced. So in transverse direction, using TFBT test, we are able to calculate how the interfacial adhesion between fiber and matrix is taking the role. Okay, for that we found that 50 voltage and 5% of carbon fiber nanoparticle gave us the optimum result, that is 35 megapascal. And again, you can tell me, oh, it is very poor mechanical properties, 35. Yes, it is very poor, but this testing was just to confirm at what voltage this higher interfacial adhesion is taking place. But generally, if you want to measure the tensile strength, we do the testing along the longitudinal direction. Okay. So another technique that is very, very faster, because whatever they develop, whatever technology you develop, that should be industrialized also. So for that, electrospray deposition technique is one of the technique where you're in the needle, this kind of syringe, in that you have the resin and the CNT dispersed. Okay. So once you using this adjustable or movable plate, once you use any pressure, then this resin will come outside, and here is a roving of your glass fiber. Okay, so on the surface, once it comes out of this needle, and between this needle and this glass fiber, there is a very, very high voltage. Okay, you can apply. So if you apply any high voltage, the spray of that resin will become umbrella shape. I mean the jet of resin will become umbrella shape, or very, very micro spray of the resin will be there. So it will get easily deposited on the glass fiber. Okay. So this kind of a design you can prepare in your lab also. This kind of setup you can easily do. Why? Because if you can easily change this x-axis and y-axis, and you just keep on unroving the glass fiber, we can completely make this system automated. Okay. So any system which is automated, there is a high productivity and there will be high demand in industry. Okay, so this kind of electrophoretic deposition technique also you can see This is a pure glass fiber, and this is a CNT, carbon nanotube deposited glass fiber, and you can see there is a huge change in surface roughness. And if you can add surface roughness on carbon fiber, there will be high mechanical interlocking with the matrix. And higher the mechanical interlocking with the matrix, higher you can expect the better mechanical properties or tensile strength of the composite. Okay, so here you can see at near about voltage. Here also voltage play a major role near about at 30 voltage, and CNT here was taken near about I have not mentioned here. It was something 5% only. Yeah, I forgot to mention here. So at 5% and 30 voltage, it gave a very huge enhancement in the flexural strength. So these three, one is electrophoretic deposition, another is electrospray deposition, another is nano modification of the epoxy. That three part I have discussed. This has a huge potential for the industrial application. Now coming back to the example of graphene, although we have taken the graphite nanoparticle, those are small particles, but the exploration of graphite nanoparticle was very difficult. But nowadays you can see there is a huge application of graphene. So here we have taken some graphene nanoplatelets and we tried to modify their surface and using different oxidation time, different oxidation temperature, and we optimized that. And here we found a very interesting point. Some of the people who are working in this graphene, they know that the synthesis of graphene is very tough. Single layer graphene, although you have within your battery, you have some graphite rod that is also made of graphene, but you will not get any good properties of the graphite rod. You will get a good mechanical, electrical, thermal properties of graphene only when you can exfoliate graphene up to single layer or double layer of graphene. So for that, if this figure, you can see this is a agglomerated graphite nanoplatelet. But this figure, see, you can see single layer of graphene can be seen. So with increase in oxidation time, the second figure B, where you can see some cracks has been generated on the surface of the graphene nanosheet, and with further increase in oxidation time, those gets exfoliated. Why we need exfoliation? Because to get a better surface functionalization, first we need the exfoliation. Okay, so we did a lot of XPS analysis, X-ray photospectroscopic analysis. This is a sensitive quantitative spectroscopic technique that measures what are the elements present on the surface. And if you have any material, suppose A, and on their surface any unknown material X is there. So if you do this characterization, XPS spectroscopy, you can find it out what is the unknown material is present on the surface. So this also we have done, and we found that this surface of this are successfully functionalized with amine or epoxy agent. I'm not going in depth of this because it will, and then I will not be able to cover up within 1 hour. So again, we did atomic force microscopy. We measured what is the thickness of this graphene sheet, and we found that with increase in oxidation time, we have varied the oxidation time as 12, 48, 60, 72, like that. We increased the oxidation time, and at 60 hours, we got near about 2 nanometer thickness of graphene sheet. Okay, but on scanning range, you can see this kind of zigzag nature. Why? Because during exfoliation, we are also adding the functional groups on the surface. So any silane group, if you add on the surface, those will give this kind of nature. But with increase in further oxidation time, so what will happen, you will see that there will be a lateral breaking of the particle of the graphene. So you cannot give a very high time for oxidation, because if you give high time, there will be lateral breaking, and if lateral breaking takes place, that material will be having high surface energy, and they will again form the agglomeration. So for that, our optimum result was 60 hours followed by selenization. Okay, so we also found how to quantify what is the interfacial adhesion between the carbon fiber and the matrix material. Okay, for that we did the nano indentation in IIT Kanpur. So this nano indentation, we did the indentation along the transverse direction of the carbon fiber and matrix. So where we did the indentation on the matrix and approached the carbon fiber and then passed the carbon fiber. So, and we also calculated what is the nanomechanical properties. Nano indentation means it is nothing but a hardness in nano level. Okay, nano hardness you can say. So this nano, you will say the nanomechanical properties, once it was on the carbon fiber, the mechanical property, nanomechanical property was high. But when it comes to the matrix material, the nanomechanical properties will be low. But there is a sudden change in mechanical properties, and this the interfacial zone where the sudden change is going to take place, that zone is nothing but the interfacial zone of your fiber and matrix. Okay, that is the interfacial zone of carbon fiber and matrix. So along this interfacial zone, so if you see the neat epoxy, okay, without any modification, without any surface functionalization of graphene, if you check it, the interfacial properties are low as compared to the, maybe I have given, yeah, I have given here. So this is without any graphene, and this is with graphene. So this, the middle images, these two images are showing the interfacial properties. Okay, so where the interfacial properties of neat epoxy was something lesser, but in case of selenized graphene, the nanomechanical properties has been enhanced significantly. Okay, so this tool also gives the measure that how we can improve the interfacial adhesion. One was TFBT test, another is nano indentation test. These two tests is very useful if you want to measure any interfacial adhesion has taken place or not mechanically. Then you can go for this. Then we measured this kind of tensile test, and we found that 60 hours, obvious, because 60 hours was highest exfoliation, and only 0.5% of graphene was sufficient to improve the mechanical properties from tensile strength. You can see the tensile strength of any CFRP is only 855 megapascal, but in case of this selenized graphene reinforced CFRP, it is 1685 megapascal. So this is almost 4 times than the steel, and but this is having very lightweight. Okay, so this technology was very helpful to improve the mechanical properties, in plane or out plane mechanical properties. Now coming back to the biocomposite, as you know that any material, if the matrix and fibers are biodegradable, then the composite prepared out of those components, we call it biocomposite. I will not go in depth because you already know the fibers may be bamboo, flax, canap, hemp, sisal, jute, coir. These are some different types of biocomposite. And what are the properties of this biocomposite? Out of these different biocomposite, I have chosen bamboo because I have worked on this topic, that is bamboo from composite. So the bamboo composite is having organic and biodegradable, high tensile strength, and it can be harvested annually because we have lot of source in northeast part of India. We have lot of bamboo forest. We can easily have them, harvest them. Okay. So 8.6 million hectare of bamboo forest in India. So better yield is there. You can easily extract the bamboo fiber. So this is the process through which we prepared the fibers from the bamboo. So first we took the bamboo, then we prepared chips of bamboo, then we extracted the cellulose. Okay, so actually bamboo itself is a matrix, is a composite, having cellulose as the matrix and lignin. Lignin is the matrix and cellulose as the fiber. Okay, so once we do the alkali treatment, the matrix material will get removed and only fiber you can extract. But this is having high agglomeration tendency. For that again we have to do some surface functionalization like benzoylization or selenization. Those also will help to get de-agglomerated bamboo fiber. I will skip few of them. You can see this figure, middle portion, you can see before the functionalization and after functionalization, the surface property of the bamboo has been significantly changed. Okay, so if you get a surface is coated with this APTS or benzyl group, then it will not get agglomerate with the nearby bamboo. So we can have a carbon bamboo micron fiber in a very separated way, and you can easily disperse them in the matrix material. Okay, so we can also add some kind of nanoparticle on the surface of bamboo, like a CNP can be deposited on the surface of bamboo. As you can see that those will be helping to improve the mechanical interlocking with the matrix system. Okay, next we can take the help of your ball milling to convert the bamboo microfiber to bamboo particles, okay, bamboo nanofiber or bamboo particles, because these long fibers you can break it and get the powder form of the bamboo micro, and these powders can be used for preparation of the composite, and this way also you can have a better mechanical properties. So these are some research areas, because our intention is that what are the research scopes that we have in this in this surface functionalization, and you can take any source material and you can prepare their composite with a certain goal, okay, because we Indians, we have a bad properties is that first we do the research and go for searching what may be the application, so that nature we should change, and we should first decide what will be the application, then accordingly choose the raw material and select the functionalization method. Next, coming back to the very important topic, that is smart self-healing composite. For this composite preparation of this composite, we need to know the surface functionalization techniques, and that's why I have shown all these slides. Now coming back to the self-healing, what is it actually? So this self-healing, whenever our body gets cut or any injury, you can see that it heals automatically, right? So same thing, whenever there is a crack in a material, it has the capability to heal the cracks. So this is a bio-inspired mechanism derived from nature, and for this kind of mechanism, first invented technique was by Illinois University Software Group. They invented this technology using microcapsule based. Okay, I will discuss them. I have given this figure here. So whenever in case of FRP or CFRP composite, what is our motivation is that, so first of all, in case of composite also, first failure, suddenly the material does not fail. First, what will happen during preparation, there will be some micro voids or some cracks will be generated in nano or micron level. Then those micron or nano or micro cracks will be propagate to get a large scale, and finally there will be catastrophic failure. Now our motivation was that if you can arrest the micro cracks in their nano or micron level, then we can maybe that enhance the lifetime of the material. So due to that, we derived this bio-inspired self-healing mechanism for CFRP composite, and you can see this is the figure that I have shown, where if there is cracks in a laminated composite, you know there are so many laminates are there, and if generally the failure occurs due to interlaminar delamination. So if you take the advantage of self-healing, just keep this cracked particle in oven, it will get healed by itself. Like if you keep some sunlight, under sunlight, it will get rebonded. These cracks will be vanished automatically. Okay, how? That is what we are going to discuss later. So first technology what was invented was the microcapsule based technique, where your resin and hardener, one capsule was containing the resin and another microcapsule was containing the hardener. So whenever any cracks propagate through this capsule, so what will happen, this crack will be broken, and this microcapsule will be broken. So along the crack path with the resin and hardener will come together, and finally your crack will be healed. Okay, so this is the technology Software Group developed, but this is a single time healing. Once it healed once and again the crack propagates through the same surface, it will not get healed in the next cycle. But in my PhD thesis, we have developed for the first time multi-times self-healing capability without any external intervention. Okay, so how the capsule has been synthesized, that is again another topic. I am not going in depth, but I will just call the technique as solvent evaporation technique. Solvent evaporation technique. So I will just give a brief introduction how we prepared microcapsule. So this is oil, this is water. Those will form a two layers. Those will not get mixed. Once you make the stirring, the bubble water oil droplet will form in the water. But when you give sufficient time, those will be again separated, right? But when you add a surfactant, okay, what is surfactant again? Surfactant have one end hydrophobic, another end hydrophilic. Okay, so one end it has a good friendship with water, and another end it has a good friendship with your oil. So if it is there on the surface of the oil, so what will happen? This end, since it is having good friendship with the water, so once you get a good surfactant on the surface of the oil droplet, it will not get separated again. So this technology is very useful for preparation of the microcapsule. So microcapsule technique, lot of applications are there for drugs delivery, lot of applications are there. I have also used this microcapsule for self-filling of adhesive joint. Okay, so in the adhesive joint, in the resin system, I have added hardener containing and epoxy containing microcapsule, mixed them and incorporated on the surface of the substrate. Okay, so once it was joined and once I tested the sample, it was broken. Then I just kept the sample with some predefined pressure. It again got rebonded. Okay, it again got rebonded. That is the beauty of self-filling. But still, this is single times. Okay, once it got rebonded, second times you cannot get the healing from this mechanism. That is the disadvantage. Okay, so this stirring temperature to get reduced size of the microcapsule, also you can change the stirring temperature, okay, to get a different size of the microcapsule. So this microcapsule is a spherical ball. Inside of this, your core content will be there. Either it may be the resin or it may be hardener. Okay, so I will go a little bit faster. Then this is the adhesive joint where along this line we applied the smart adhesive on the surface, and once we apply the load, it got broken, and once we take the two substrate again kept in the same position and give a small pressure, it was able to rebond, and again we got the same mechanical properties. Okay, so we got a healing efficiency up to near about 90%. Okay, 90%. And what was the microcapsule content? At 10 weight percentage of resin and hardener, we got a 90% healing out of the material. So how we calculated healing? First we tested the material broken. So we recorded what was the interlaminar shear strength, ILSS. That is called ILSS in case of lap joint, ILSS, interlaminar shear strength. Next, once we healed and again tested, so those after healing what was the ILSS and before healing what was the ILSS, the ratio is nothing but the fraction at what extent it was able to recover the ILSS. So if you multiply with 100, that is the healing efficiency. Okay, so our team was able to get winning from ZED Project Challenge in 2014. Okay. They were able to get this, our team to get this, I mean they got the first prize out of India for this project. Okay, so you can see I prepared some, not only adhesive, I prepared some composite also. When it gets broken, it once you join these two samples and give some heat, it will again rejoin, and even you cannot see where actually the piece was broken. That is the beauty of this technology. But sorry, but this is very disadvantage is that only single time healing can be done, and after healing there is some degradation of the material like this. So we left this technique, we developed a new technique. Okay, so we also tested the scratch on the surface and see seeing that yes, the self healing was possible, because this is the scratch before healing and this is the scratch after healing. The size of the scratch has been tremendously reduced. Why? Because it is with time it is healing the surface. Okay, so from the scratch test also we were able to get the healing visually, but we were not able to quantify. Just we can visually compare the results. Okay, on the high resolution microscope FESEM, we have seen that due to breaking of the microcapsule, some resin and hardener has flown on the surface. These are some resin and hardener weighted zone you can see, and these are the region. These are the reason behind our self filling that is going to take place. Okay, so whatever the technology that I have shown, that was single technology. Now we have used a DL-Felder based chemistry. Okay, DL-Felder chemistry. What is DL-Felder chemistry? There is a die-in and dienophile part. Whenever they form a bond and form DL-Felder adduct. Okay, so those DL-Felder adduct, if you apply, if you using any mechanical properties, you break that bond, just keep them nearby and apply heat, they will again reform the bond itself without any external intervention, without any pressure requirement. Okay, so this bismaleimide, DL-Felder adduct if you can add on the surface of nanofiller, then we can have multiple times the healing capability from the polymer composite, or even we can apply them for CFRP composite, because our final intention was to test them in CFRP composite. So first we started from polymer, then we applied in CFRP composite. So what is that? For that we have prepared a hybrid resin system. Okay, one is thermo reversible resin, another is thermo irreversible resin. Reversible and irreversible, you should understand. Whatever reversible means, it will break bond when apply heat, it will reform bond when you pull down the heat. That is thermo reversibility. And thermo irreversible, it will not happen when you apply heat and pull down. Okay, so this dismelamide and thermo reversible and thermo irreversible, this if you can add on the surface of graphene, okay, and the thermo irreversible if you can add in the matrix system, so those will have a bonding. And this bonding, whatever I am showing here screen, this is the Diels-Felder adduct. Okay, this Diels-Felder adduct, once you break any material made of this kind of carbon fiber, carbon filler based composite, this chemical functional group will help to create a rebonding with the other fractured surface. Okay, so that is what we prepared. For that we functionalized the graphene with this bismillamide. For that, again, to add bismillamide, first we needed to functionalize with the amine group and epoxy group, and finally we were successfully able to add this bismillamide, and that's why I have shown the functional groups. Those steps. So we characterized those functionalized ZNP. Okay. So suppose furfuryl amine functionalized ZNP. This is furfuryl amine is the die-in part. Again, I have to go to the previous slide. There is two parts. One is die-in and another is dinophile. Okay. Furfuryl amine is your die-in and bismillamide is dinophile. So we need to functionalize graphene with both die-in as well as dinophile part. So that's why first we functionalized with furfuryl amine and we checked the chemical characterization and found that yes, functionalization has taken place. We also did the XPS analysis. We found that yes, surface functionalization has taken place. Then we checked how the mechanical properties has enhanced of this kind of nanocomposite. If you prepare the nanocomposite of this furfuryl amine functionalized and dismillamide functionalized graphene based polymer, then how it will behave. So we have seen that yes, it was able to improve the tensile strength also. So you can see the tensile strength was improved by 43.58% and modulus was improved by more than 100 times. Okay, the two-fold increasement was observed. So till now, whatever the literature, it was found that if you add any self-healing property in any material, the mechanical properties reduces. But we were for the first time able to add self-healing as well as improved mechanical properties, and that's why we were able to file a patent on this work. Okay, next is we also tested the self-healing properties. This is flexural strength. We also got some enhancement. I'm not going in depth. Why? Because this enhancement was done there because the bismillamide on furfuryl amine functionalized graphene were able to form covalent bonding with the matrix. Okay, due to that we were able to get this kind of enhancement. We also prepared a carbon fiber. First we tested in nanocomposite, then we prepared the CFRP composite and found that same thing, CFRP also, we got this enhancement. Then we tested the out-of-plane mechanical properties and we also found that there is a huge enhancement in the flexural properties, like 63% enhancement was there in out-of-plane mechanical properties. Then we tested the double cantilever beam. So this is the father of this technology where you can see double cantilever beam we tested as per ASTM D5528. So what we did using this double cantilever, having some predefined crack path using some Teflon sheet, we first incorporated delamination intentionally with an intentional crack path. First we gave the delamination, we recorded the crack path propagation using high spectroscopic, high speed camera. We recorded the crack path, we noted what is the peak load that can be enhanced for this kind of crack propagation. Okay, after that, we what we did, we again healed the sample and again tested. So after healing, what is the interlaminar shear strength, and before healing, what is the interlaminar shear strength? Comparing them, we were able to calculate what is the self-healing efficiency. Okay, so this is the self-healing efficiency. You can see this is mode 1 fracture toughness. It is called whatever the strength that you get from DCB test, double cantilever beam. That is called mode 1 fracture toughness. I cannot cannot go in depth of this. You will get easily from ASTM standard. What is this? What is that? You can easily get this thing. Okay, what is Z1C? Z12. It is mode 1, mode 2. There are 3 modes of failure: mode 1, mode 2, and mode 3. So what are those? This was mode 1 fracture toughness. Okay. So we got the healing efficiency 87%. And what was the most important thing is that we were able to get repeated times of healing. But with number of cycles, the healing efficiency got reduced. That is again till now one disadvantage. But still up to 9 times we were able to get the healing efficiency. Okay, 9 times we got the healing efficiency. And you can see this is the cracks before healing. This is the crack. This is the cracks what appears after healing. The cracks has got vanished once you apply any heat and you add the technology of self-healing. Those cracks got vanished, right? But it depends on what is the hybridization percentage. As I told you, I prepared a hybrid matrix, right? Thermo-reversible and thermo-irreversible depends on what is the amount of thermo-reversible matrix present in the system. Depending on that, you can have different extent of healing. But again, if you give very high amount of thermo-reversible matrix in the system, what will happen? Mechanical properties will get reduced. So we have to take both the thing. We have to improve the healing efficiency as well as improve the mechanical properties. But in general, mechanical and healing properties have trade-off nature. If one increases, another decreases. So a proper balance is required for them. Okay, so for that we need a lot of parameter variation and lot of optimization to get a better result. And for our case, we got 70% DL cylinder resin and 0.5% of filler can heal up to 87% healing efficiency. Okay, so I will stop here because if I go for substrate functionalization for adhesive joining, I will not be able to cover this thing. So this is again different application of surface functionalization. Okay, so I will skip this adhesive joining and how the surface functionalization helps in adhesive joining. Okay, so this small 2-3 few slides were there, but what are the conclusion here I have got is that functionalization of nanofillers through single step process have a great future. Okay, what was our problem is that whatever the processes we have developed, these were multi-times healing. I'm extremely sorry. Those are multi-steps functionalization process. And any process which is multi-step and chemical route based, those are not welcome in the industry. Okay, so you have to develop a technology of surface functionalization like cooking in a pressure cooker. Everything you give in the pressure cooker and finally you get the food ready. So that kind of technology, if you can develop, maybe it will be a great contribution to the scientific society. Next is conversion of lab scale to industrial scale for green methods. So we should not use any acid or any bases or any some other carcinogenic chemicals. So this we have to take care. Okay. So if you develop any technology without using those carcinogenic chemicals, maybe it will be having a great application. And again, I would like to inform you that graphene till now lot of research scopes are there. You can go for graphene and you can go for functionalization graphene. You can go for different applications. Then in case of smart self-healing application, till now whatever the healing required, I needed some temperature, okay, for getting heat. But if you can develop a completely room temperature, like Motorola and some other company have already developed one technology. If there is a scratch on the surface of your screen, mobile screen, that will be automatically healed. Okay, those type of healing is very much required. But although they have demonstrated for those kind of applications, but structural application and healing at room temperature till now, no one can be able to develop. Next, you should be able to get healing as well as better mechanical properties. This metallic substrate, this since I have skipped due to the time limitation. So I would like to take this session open for the audience. If you have some doubt, you can ask here.
For your nice presentation. Actually, the time is college closing time right now. So maybe most of the faculty members as well as the students, they are in hurry to go to home. So actually,
Right.
yeah, actually, if anybody have any doubt regarding whatever sir has discussed, please mail me. I will forward it all the questions to the Khan sir, and he will definitely try to give.
Yeah, I will try my best to respond those queries.
Okay, thank you, Dr. Khan sir, for speaking to all the participants about this interesting topic. And those has attended this webinar, they really enjoyed your presentation. So we appreciate you for the time devoted towards us from your busy schedule. And thank you once again for your time and cooperation. Thank you, sir.
Thank you so much, Dr. Bhumi.
Okay,
Thank you.
Thank you, sir.
Thank you.
Okay, sir. Now
I can leave, right?
Yeah, sure. You can leave. The certificate I will send it very soon.
Okay, sure.
Okay, thank you.